Ladies and gentlemen of BlueHat 2025, trust nothing.
Hello, BlueHat. Hello, BlueHat. It's a pleasure to be here. I'm Arad Cohen. I love cybersecurity, hyped about LLMs, and today we are going to use LLMs to break things. I have an issue with clicker. So yes, my name is Arad, also known as Aradko. I have over 7 years of experience in security research and development. Today, among other things, I work in the Cyber Education Center as an instructor and mentor in the Makshimim program, the National Cybersecurity Program for high school students. And yes, this is how ChatGPT predicted I will look like today. When I say LLMs, or large language models, I mean models like GPT-4 that power tools as ChatGPT. And before we'll start, I want to ask you a question. By raising your hands, who thinks that in 3 years from now, a significant percentage of the security vulnerabilities will be found using LLMs? Okay, this is interesting. So my goal today is to convince, and especially those of you who didn't raise their hands, that LLMs will play a significant role in finding vulnerabilities in the upcoming years. Because here's the thing. Everybody is talking about coding with LLMs, but almost nobody is talking about finding bugs with them. And for me, this is where it gets interesting. So our story begins with fuzzing. Fuzzing is a technique for finding vulnerabilities with brute force. It works by sending semi-valid inputs to a program to uncover crashes or unexpected behaviors. Over the years, a lot of zero-day vulnerabilities discovered thanks to this method. And let's see how it works. So imagine that we have a binary. For example, an image parser binary. So we start sending images to it. We start with a valid image, and the binary works as expected. We continue with a slightly corrupted image, and the binary still handles it. This is where it gets interesting. We can track the code coverage. The code coverage is a metric that tells us which parts of the code got executed. Think of the program as a giant maze, and each input has someone walking through it. The code coverage can tell us which paths were taken, or which parts of the maze or the code remain unexplored. So thanks to the code coverage, we can understand which new input discovered a new logic path in the code. So we can continue to send corrupted images until we might get an edge case that will cause the binary to crash. If we found a crash, it means that the binary didn't handle the input correctly. So we need to investigate the root cause of it. Is it a security bug? We analyze the issue type, buffer overflow, use after free, and whatever it may be, if it's real, we document and report about it. So now we want to bring LLMs to this fuzzing process to make it better. But before, we need to dive deep into the anatomy of a good fuzzing engine so we can understand what we can do better. So imagine that you did a git clone to your favorite open source project, and now you have a library, and this time we are dealing with a library. And libraries can't run by themselves, so we need an executable that uses this library somehow. This executable becomes our interface to the library. In fuzzing terminology, this is called the fuzz target. Next, we need a set of valid or semi-valid inputs. These are the starting point from which we will generate new inputs to test the library. We will do so using techniques like bit flipping, incrementing bytes, or decrementing bytes. This is where the harness comes in. The harness is a component that's responsible to take inputs from the seed or corpus, the initial set, mutates them, and send it to the fuzz target to activate the logic in the library. And then we saw that we have two options. If we are lucky, we get a crash. And if we don't, we still gain something. We can track the code coverage. And that creates a feedback loop. If the harness took an input, mutate it, and send it to the fuzz target, and it discovered that the code coverage increased, it means, OK, this is an interesting input, so it can add it back into the corpus set. And over time, this will help to increase the code coverage. And fuzzing is an art, and code coverage is the most important thing. With better feedback loop, we'll get better code coverage. With more and different fuzz targets, we will get better code coverage. Same for the corpus, or the seed, the initial set of inputs. With better corpus, better code coverage. And most importantly, with better code coverage, there is a better chance to hit a bug. Because a hidden bug will not reveal itself until the code it lives in gets executed. Now to the fun part. How we can use LLMs to make this process better. So let's first explore a few solutions. Last year, I came across a tweet by a guy named Brandon, an AI researcher at New York University. And he did a fascinating experiment. He took a small C library that parses GIFs, and he sent it to his favorite LLM chat, in this case Claude, and asked Claude to create a Python function that will generate random inputs to test edge cases in that library. And the results were impressive. He got really nice code coverage and even found 4 memory bugs. This made me realize that, OK, LLMs becoming better and better in code, and they actually can help us to find bugs. So what did Brandon really do here? This is the fuzzing flow we saw before. And Brandon didn't care about the code coverage or the corpus. Instead, he used LLM directly into the input generation. And you might say, OK, this is just a tiny library for parsing GIFs. And you are absolutely right. So let's move on to something even more exciting. Google OSS Fuzz. OSS Fuzz is a project by Google open source security team. Originally launched in 2016, it's a continuous fuzzing service for many open source projects aimed at making the internet safer. The guys from Google invest millions of CPU hours to increase the chance to hit a bug. And here's the interesting part. In August 2023, they published on their blog that they had started experimenting with LLMs to gain more code coverage and to find more bugs. I was really curious how exactly they are doing this. And in a minute, we are going to see just that. But then, silent. For almost a year, there were no updates until November 2024. Google announced that OSS Fuzz, now powered by LLMs, discovered more than 25 vulnerabilities, including one critical in OpenSSL, which is the most popular implementation for TLS. And it's a top target to find vulnerabilities in. And as we will see, it's a hard target to fuzz. I think that you can't ignore something like that. I saw the update and I was like, OK, they are really onto something. So let's see what Google did here. This is the fuzzing flow we saw earlier. And Google's solution was to use LLMs to create a lot and different fuzz targets. Usually, you would need to write them manually, which doesn't scale well. And by letting the LLMs to handle all this, they saved a massive amount of time. And because fuzz targets are simple and short programs that just use the library we want to find bugs in, the LLMs can handle it. I saw this, and I wanted to take a different approach. I wanted to go further. I want to build a full LLM-driven fuzzing flow. So we saw that the guy from Twitter took LLMs directly for the input generation. And we saw that Google used LLMs to generate a lot in different fuzz targets. And I thought, why not to take fuzzing's most powerful weapon, the feedback loop? I believe that by using an LLM, we could analyze the code coverage and error logs better and to understand how to create better inputs, the ones that will push deeper and deeper into the code coverage of the library being fuzzed. So now, we are going to build just that. But before, let's talk about TLS. I like the fact that OSS Fuzz found a bug in OpenSSL. So I wanted to focus on that too, specifically on the TLS handshake. TLS is one of my favorite protocols, and I will not dive too deep into it. But at a high level, this is the protocol that encrypts the web. This is the protocol that turns HTTP into HTTPS, and you use it dozens of times a day, every time you go online. At the beginning of the TLS session, which works over TCP, the client and the server first exchange keys, agree on which cipher, hashes, key exchanges, signature algorithms they are going to use, checking each other's identity, checking integrity that no one tampered with the messages, and establishing the keys for the encryption. And if you didn't quite follow all the TLS flow I've just mentioned, that's totally fine. What matters is this. The TLS handshake is complex and unforgiving. Even the tiniest mistake can cause to the termination of the handshake, and this will hurt our fuzzing effort. So let's fully understand why the TLS handshake is hard to fuzz. First, it's stateful and interactive. Establishing the handshake requires a specific sequence of messages, each dependent on the previous ones. So you can't just send one random message and expect progress. It's a dance. Another thing is that TLS is full with integrity checks, hash checks, signature verification, certificate validations. And when we fuzz, we add a lot of randomness, to test edge cases. And this might hurt all these integrity checks. And this might block us when we fuzz. Another thing is that TLS is a network protocol, which is over TCP. There are solutions to fuzz network protocols, but this still adds complexity. And lastly, TLS is designed with extensibility in mind. Over the years, a lot of ciphers and fancy extensions have been added to it. So in order to get a deep code coverage, we need to activate all the logic for all the extensions in their edge cases. So yeah, TLS is tricky. And if we want even more motivation, let's see the status of, fuzzing OpenSSL. Lucky us, the guys from Google let us watch all the fuzzing reports for all the projects that are under fuzzing. So let's see. First, let's take a library that is an easy target to fuzz. So I took the libexif library, which is a library for parsing images metadata. And because it's stateless, it just gets image and returns the results, it has a solid code coverage. I'm talking about line coverage, 83%. On the other end, in OpenSSL, well, you can see about 42%. So OpenSSL, as you can see, it's a huge code base. So if we want to focus specific on the TLS handshake, we have about 52%, which is still low. I think that the fact that one of the backbones of the internet has such a low code coverage, well, this is a red flag. And you might ask, okay, what about other TLS implementations? And well, you can see the situation for them. Cool. Now, we have a vision. We want to build a full LLM-driven fuzzing flow. We saw the motivation. This is hard to fuzz the OpenSSL, and this is highly, it's a tough target to find the vulnerabilities in. So we can take the OpenSSL library, and the first thing we will do is to write a TLS server. A simple C program that uses the OpenSSL library. Next, we can create a small TLS client, basic and intentionally incomplete TLS client that will each time try different handshake configurations, different ciphers, different extensions to get deep code coverage and to get edge cases. We can write it in Python. Then we can run this client, let's say, for about 1,000 connections per run. After that, we can collect all the code coverage and the error logs from the handshake in the server side. Then come the key part. Analyzing all the code coverage and error logs, and our target is to identify what I like to call code coverage blockers. Parts of the code that prevent us from reaching deeper, and it blocks us to reach better code coverage. For example, this snippet is from the OpenSSL state machine. And as you can see, the TLS server will only accept certain TLS version and will reject deprecated ones. So yeah, this blocks us. If our TLS client is very basic, every time it initiates a connection, it just picks random TLS version, so hopefully it will get nice code coverage. This might block us. Cool. After we spot all the code coverage blockers, we have two options. The first is to improve the TLS client in Python. And the second option is to patch OpenSSL. I mean, change the actual code from OpenSSL and then recompile it again. This is useful in cases, when the TLS has many integrity checks, certificate validation, signature verifications. So we might want to skip them and continue fuzzing. And then we said that we want both the decision-making and the actual code improvements to be handled by the LLM. After that, we will run this TLS client once again. So hopefully, with each iteration, we will get better and better code coverage. So this is the flow we want to achieve. But yeah, this is nice. But actually, we have a lot of problems. First, LLMs aren't magicians. In order to give us meaningful output, they need the right context. They need to understand what's going on. And the issue is that, OpenSSL is almost 1 million lines of code. And the prompt sizes are limited. So we need to come up with a way to send only the relevant context to the LLM. Another thing is, how do we patch OpenSSL? OpenSSL, it's written in C, and we need the LLM to write the changes in C and then recompile it again. Another thing is, how do we export all the code coverage? And how do we get all the errors from the handshake so we will be able to track all the code coverage blockers? So yeah, it's like a puzzle, and we need to create a POC, or a proof of concept. So let's start with the context. We saw this code snippet, and TLS has evolved over the years. But here's the thing. Only the last two versions, 1.3, 1.2, and 1.3, are still supported. The rest are deprecated. So if our TLS client is very basic, every time it initiates a connection, randomly picks a TLS client, after one iteration, it's clear. It's a waste of time. This version mismatch blocking us. So what do we want? We want to send it to the LLM. And so he will, make our TLS client better, fix the TLS function in our code. So we can ask him just that. But they need context to understand what's going on. And specifically, the LLM probably needs this function. This function probably holds the context it needs, so it can understand which version are allowed. But how do we know? How do we know which functions to send to him? This brings me to a really nice feature in the LLM world, function tools. Function tools give us the option to define tools the LLM can use when needed. For example, we can give the LLM this tool. This tool will allow the LLM to pull every function it wants from the OpenSSL code base. Let's see this in action. So we send the LLM this code snippet, right? We says, please improve the fuzzer, please improve our TLS client. But the LLM says, no problem, but I need more context, right? I need the SSL choose server version. So we use the tool we gave him, and we can supply the function it needs. Think about it for a second. The LLM didn't just spit out code. It stopped for a moment, understood that it needs more context, and activated the tool we gave him. That's not just autocomplete. That's thinking like a real researcher. And the most mind-blowing thing is that under the hood, it's all based on probability, linear algebra, and calculus. And of course, to supply the tool for fetching each function it wants, we need a way to parse all the OpenSSL code base. So I use TreeSitter, which is great for parsing source code. Our next challenge is how do we patch OpenSSL? Let me show you why. So we said that TLS is full with integrity checks, certificate validation, signature verification. And for example, after keys are exchanged, every message comes with a cryptographic hash to ensure that no one tampered with the messages. So we can see this hash check right here. And this might block us because, as we said, we fuzz, we add a lot of randomness, we want edge cases, and this might, the hash might be invalid. And if the hash is invalid, this will block us because we will reach this error. One solution is to patch OpenSSL. I mean, change the actual code from OpenSSL to remove or to bypass this check. But for now, LLMs are better in high-level languages like Python and JavaScript, and this paper shows it. And in addition, the code we change need to be compiled against all the OpenSSL dependencies, and this is a headache. I struggled a lot with this problem until I came up with a solution. So I want to talk about Freda. Freda, it's an instrumentation tool. It injects V8, Google Chrome's JavaScript engine, to a process of our choice. And then it let us hook JavaScript to change the behavior of the process in runtime. And if you are not familiar with hooking, this example will clear things up. We have this code snippet, as we saw earlier. And we can send it to the LLM and ask him to please create a Freda hook to bypass the integrity check and prevent the execution from reaching this error. And we got this hook. And as we can see, this hook replaces the return value of the cryptomem compare function to be 0. This will change the condition here, so we will not reach the error, and the code coverage blocker is gone. I think the fact that LLMs can generate hooks that we can inject into a running process and change its behavior on the fly, well, that's something. And why I used Freda? Well, I could use, other instrumentation tools. But I use Freda mainly because the hooks can be written with JavaScript, and this is how we can avoid all the compilation and linkage errors. Next, what about getting all the handshake errors? So we said we want to create a TLS server in C, and this is the code. We can see the socket setup. We're initiating an SSL object and blah, 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 and the most important function is this. This function will print all the error messages from the handshake itself, and the key part that we can track the file name and the line number from each error, so we can pull the relevant snippet from the OpenSSL codebase, and this is how we can track all the code coverage blockers. And what about code coverage? Well, this was easy. I use GCC for the compilation. And GCC has a plugin called gcov, which allows us to export the code coverage after every run. This is the flow, this is the POC we want to build, and this is a summary of how we tackled every problem. We used GCC for the compilation and for gcov to get all the code coverage. We used that magic function from OpenSSL to get all the errors in the handshake so we can understand what's blocking us. We used LLM function tools to give the ability for the LLM to pull snippets from OpenSSL codebase on demand. We used TreeSetter to parse all the OpenSSL codebase. And finally, we used Freda to inject hooks so we will not have to deal with all the patching. I built all of that and ran it. I tried different prompts, different arguments, and I want to share some results. This is a graph. The y-axis is the code coverage percentage. The x-axis is the connections. And I configured the harness to measure the code coverage after 1,000 runs, after 1,000 connections. You can see the blue dots over here. And every 3,000 connections, the harness used the LLM flow we saw earlier to improve the code coverage. This is marked by the red lines here. And you can see the amazing thing that almost every time the LLM stepped in, code coverage improved. At the beginning, we are covering 4%, 5%, and we're stuck. And then the LLM steps in. Try TLS version 1.2 or 1.3, it says. Code coverage jumps. Few rounds later, the LLM says, patch this function, it's blocking you. Another jump. So maybe I haven't found a bug yet with this method, but we can see that consistently an improvement with the code coverage. And in fuzzing, that's everything. Because as we said, a hidden bug will not reveal itself until the code it lives in gets executed. Who is familiar with gradient descent? Can you spot the similarity? You know, gradient descent, the optimization algorithm. Every time we are taking a step to optimize our situation. And you know, fuzzing, it's like walking into a dark forest and searching for something that we can't even define. Using LLM with fuzzing, it's like going into the same dark forest, but this time with a flashlight. And before this session ends, I want to share a few thoughts. First, I think that LLMs have the potential to redefine fuzzing. I think that fuzzing doesn't have to stay black box anymore. With LLM, we can make it more smarter and adaptive. Another thing that, as you probably know, LLM are getting better and better in code. Prompt engineering, which involves knowing what to ask the LLM, giving it the right context and examples, has a significant impact on the result. I expect to see more and more new ways to how to leverage LLMs in order to find bugs. And finally, today the issue is not about who builds the best LLM model. It's about who uses it best to solve real-world problems. Because it's no longer about who writes the code. It's about who asks the question that matter. Stay creative. Thank you.